Venn diagram. You guys have worked with these before, in some case or another, right? I hope. So when I start talking about certain things of being independent events or compound events, one of the things I want to talk about was what's called mutually exclusive. Do you know what that means?
Excluded both. Sounds kind of appropriate.
What I want to think about here is, let's take our old adage of a deck of cards. And I want to figure out what is the probability of getting a jack or a 4. Bless you. The probability of getting a jack or a 4.
50.
There's 52 cards in the deck. So what's the probability of getting a jack? How many jacks are in the 4?
Oh.
13. Wait, 1 over 13.
Ladies and gentlemen, how many jacks are in a deck of cards?
4.
How many cards are in a deck of cards?
52.
How many 4s are in a deck of cards?
4.
How many cards are there? Are these completely independent of one another? Are they exclusive to themselves? There's no shared overlap between 4s and jacks, are there?
No.
So the probability of a mutually exclusive event, this would be a mutually is nothing more than the two probabilities added together and simplify the fraction. So basically I have a 2 out of 13 probability of flipping over a jack or a 4. No, I lose.
Drive to 13 cards.
Now, the difference between the wording of that and the following is pretty subtle. What's the probability of an ace or heart? Probability of ace or a heart.
There's 4 aces over 52, and there's 13 hearts over 52.
Exactly. Does everybody see how this one has an overlap?
Yeah.
Because there's an ace of hearts. So what happens here is that this is a not mutually exclusive event. You find the probability of an ace. There's 4 out of the 52. Or the heart, well, there are 13 hearts out of the 52. But you have to back out what they have in common. You're backing out the intersection of an ace and a heart. There's one of those. So you get, what is that, 16 out of 52. 8 out of 26, and that would be 4 out of 13. So we're going to work with two types of probabilities today, mutually exclusive and not mutually exclusive. If you have two events, the compound event, event A or B, and it's not mutually exclusive, it's just the probability of A plus the probability of B, and then you back out what they have in common, which is called the intersection of A and B. Whereas if it's mutually exclusive, it's just the probability of A plus the probability of B. So we're looking at, when we're writing these out, when we're reading these, it's very subtle in how it's worded. The probability of getting a face card or a diamond. Probability of a face card or a diamond. Well, how many face cards are there? When they call face cards in this book, they're calling them jack, kings, and queens. So, probability of a face card or heart. How many face cards are there?
12.
It's 12 out of 52. How many hearts are there? How many of those face cards were hearts? out the 3 of them. So that is 10 out of 26, 5 out of 13. Oh, sorry. Wait. Yes. Math is hard. Good. So the probability of a face card or a heart. 11 out of 26, almost 50%.
Yeah.
Yeah, I win. That's why I don't gamble. We'll take the 2-card pickup. Another thing that they like to do is they write it out in terms of an algebra equation. Why? Why not? In this instance here, they want to find the probability of A and B, which means it's not mutually exclusive. Since it has the intersection A and B. I'm sorry, I just realized the formula that I wrote up here, I wrote it in shorthand that you'll learn when you go to college. That should say A and B. Yeah. Have you ever seen the seen it written out as intersection and union before? It was just, bless you, it was just habit for me to write it like that. So in this case here, it's nothing more than an equation, bless you. The probability of A or B is the probability of A, probability of B, minus the probability of A and B. Fill in the blanks. 0.8 is 0.7 plus 0.2 minus something. Most of the time, you'll be able to do these in your head. What's the something? 0.1, I agree. Okay. Think of all the shuffling I'm going to do and get better at it. So let's look at a couple of card problems again. What's that? Yes, there's a one thing that you guys are going to see here in about 2 minutes, another part that was on the part question. So if I want to look at, a card is randomly selected from a standard deck of 52 cards. Okay. What's the probability it's an ace or a face card? Well, are these mutually exclusive, or are these going to have a thing to back out?
Mutually exclusive.
Did everybody see how it's going to be mutually exclusive because there's no overlap between the ace and the face card? So what's the probability of an ace?
4. 52.
What's the probability of a face card then?
12 out of 52.
So we have 4 out of the 52 and the 12 out of 52, otherwise known as 8 out of 26.
413.
4 out of 13.
Yes!
So, let's see.
Ace or face? No. Yeah.
Which kind of makes sense if you think about it. 4 out of 13 is just almost 4 out of 12, which is 1 in 3.
Yeah. Keep doing it.
Wasn't that the third try I got it?
Try it again.
Okay. Let's try the other one.
If you did it for the whole deck, you get exactly 4 out of 13.
Boy, you are SMRT. What's the probability of a heart or a face card? We just did this one, didn't we?
Yeah.
Ah, never mind. All right, well, let's make it weird then. Let's talk about it in terms of a word problem. Believe it or not, as you read it, these are very, very easy to work with. Don't write this down. This takes too long.
Last year.
Last year, company paid overtime wages or hired temporary help during 9 months. Overtime wages were paid during 7 months, and temp help was hired during 4 months. At the end of the year, they went through the records, randomly selected 1 month to check the payroll. What is the probability that the auditor will select a month in which the company paid, bless you, paid overtime and hired temp help? Which means you're looking for that intersection of the two things happening. So will this be a mutually exclusive scenario?
No.
No. So you have to start out with, well, I'm looking at probability of paid, overtime or temp help has to equal the probability of overtime plus the probability of temp, guys, and subtract out the overlap. Well, they tell you everything you need to know. How many months did they do overtime or temporary total? 9. 9 out of 12 months was how many months was overtime? It's not how we do it though, because it's, you have to talk about it for the whole. 2 out of 9 does not simplify out. Use the words of what they have there. They tell you that paid overtime wages or hired temporary help 9 out of 12 months. So probability of overtime or temporary help is 9 out of 12. Using the formula for writing out non-mutually exclusive styles, that means it's just the probability of overtime plus the probability of temporary, back out the intersection. Well, what's 7 plus 4? 11 minus what is 9? So 2 over 12 simplifies to 1 over 6. So the probability that they picked the 1 month that they use both, or a month that they use both, would be 1 out of 6. Okay. The information is right there for it. You're using the intersection formula to set those up. The union and intersection style formula. An or statement, the probability of A or B, is considered what they call a union. The intersection is the A and B. We do a little bit more of that tomorrow. Here's the one, yeah.
So that last one, so that 9 months were overtime or temporary. Or could you just said that 3 months of that would have been overtime and temporary? Because then that'd be 3 over 12, which just goes to 1 over 6. Wait, no. That doesn't go to 1 over 6, it goes to 1 over 4.
Right.
Okay. Here's what the question that came up on the part that I saw some of you guys got. You guys got a question with a symbol, probability of something prime. Did you guys see that one? That's called a compliment, and it wasn't saying that you look nice. What it's doing here is compliments with probabilities are used to do less calculations. A compliment is nothing more than 1 minus the probability of that event occurring. It's like the opposite of the event happening. So if you have a 75% chance it's going to rain, 25% chance it's not going to rain. Okay? It's kind of like the opposite of something. Really easy one to think of. Probability of getting hearts. Getting a heart would be 1 out of 13, correct? No, I'm sorry. 1 out of 4. Sorry, I was thinking 13 out of 52. So it's I have a 1 in 4 probability of picking a heart.
Yeah.
Hey, what was the probability of not getting the heart?
3 out of 4.
3 out of 4. So it's the opposite. Okay, it's what's gets you to the whole probability. Remember, probability goes between 0 and 1. The complement is the other part. Okay?
So it's like a complementary angle.
No, not even close. We're talking about 90-degree angles. These are not
Yeah.
good. I'll show you how a complement works a lot of times, like I said, to help you not have to do as many calculations. So right there is 36 possible die rolls. If you roll out 2 dice, you get all those values, 1, 1, 1, 2, and so on and so forth. It looks a whole lot like a multiplication chart. So if they want to say, what is the probability of a sum not equal to 8? That means what you want to do using complements, just to make your lives easier, is that we're going to find the probability of the sum equal to 8, and then do its complement. Well, how many of these rolls give you a sum of 8? Let's see here. 1, 2, 3, 4, 5 of them. So 5 of them give me a sum of 8. How many of them don't?
31.
1 minus 5 over 36, which is 6. What's happening here is it just allows you to do less calculation. If you think about if you had a really large data set and you had to count out a whole bunch of things, sometimes it's easier to just find the opposite of what you're looking for. It's just quicker. Okay? That's what we use complements for. All right. The sum is greater than or equal to 4. Well, instead of trying to count how many of them are greater than or equal to 4, can I count how many are less than 4? How many of them are less than 4? 3 of them. So the sum that is greater than or equal to would be 1 minus 3 over 6. And using complements a lot of times just makes it quicker. It's just a little bit easier to work with. And it's not that the fractions are going to be so scary that you can't take 1 minus something, because the common denominator is going to be pretty easy to get. Okay? Not so scary? All right, let's talk about geometric probability. We're going back a day. Geometric probability. Do you guys remember this last year?
Yeah.
Well, you should.
I remember that we did it, but I don't remember doing it.
In order to get geometric probability still has probabilities between 0 and 1. Okay. What happens here, if we're looking at this, you're going to take the area of the favorable region divided by the total area. So in this example, if I just wanted to figure out what would be the probability of getting the bullseye, what's the area of the bullseye? What was that? 9 pi. What's the area of the whole thing? What would you do?
144.
I don't know. What's the radius of the large circle? Oh, what?
I have one. I have that. Mr. Murphy. Isn't it 144 pi?
I don't know what that is. No. No, it's not. All right.
That's karma. Yeah. He says he's gonna select all.
Oh.
Did he? What did you say?
Oh.
That would not be the worst. Why didn't you get 3? That would have been so cool.
It was supposed to do that. It doesn't work very well with the suction cup. I need to get something better.
You should like tape one of the markers to it.
Work on your form.
Yeah. That was cool.
should actually get a
Did you make
bonus.
this yourself?
What?
See how fast they flinch?
What? What's scary?
Shoot him.
Oh, shoot Drake for that. You're so scary.
What's that? Hours of entertainment.
I am the captain. I am the captain. No time for losing, 'cause I am the captain of the world.
Is that Murph's audio recording?
It's Homer Simpson.
Oh, I thought that was
Alright.
I thought that was you.
So, remember, when you're working with some of these things, you might have to find the donut hole. You might have to find and back stuff out. For example,
Oh dear.
I want to find the probability of the shaded region.
No.
Yes. Perimeter active. Yeah. Perimeter active stuff. It's a regular hexagon inscribed in a circle, which means I need to find the first of all find the area of the shaded region, and then divide it by the total area, which means, well, what do you remember about hexagons? 6 sides, yes. There's certain angle stuff.
Are you gonna make it
What does the apothem do to a side of a regular polygon? Cuts it in half. So I know I have an 8 and an 8. I needed to redraw this in to find that angle. Do you remember how to find the angle measures in regular polygons? It's a weird formula, okay? Help me out then.
180 and minus
Yeah. N minus 2 times 180 over n. Then I'll give you each one of those individual angles.
That number of sides.
Yeah. When we do that, you're going to get 120 for that whole angle. The radius, going from the center to that vertex, bisects it. So in a hexagon, you wind up with 30, 60, 90 triangles. If opposite my 30 is 8, what is opposite my 60? It wasn't that long ago. We just did trig a couple months ago. 8 root 3.
Why did I say root 2? I mean,
And then what's the radius? 16. So to get the area of the shaded region, I have to take the circle, subtract the hexagon, 16 squared pi, minus 1/2 the perimeter, which is 6 times 16, times our apothem, which is 8 root 3. I'll be there. We'll be on this test this week too. All over 256 pi. That's 16 squared. Okay. The tricky stuff here is remembering some of your surface area.
Is that gonna be the formula sheet?
Yeah, perimeter apothem, yeah. Okay. Yeah.
what's with the 256 pi?
What's 16 squared?
Oh.
Then find the geometric probability of landing in the shaded region. I find the area of the shaded region, because that's my favorable, and I divide it by the overall area, which was the circle. Okay. So you're just going to get some really crummy looking number. Remember, when you're working with geometric probability, it's a lot of just going back into geometry and what you remember about your shapes. Okay.
What if you don't remember any?
There's a somewhat small formula sheet floating around here somewhere. Yeah. Okay. This is the 12-3. That's the 12-4. You guys had to play a little catch up with the 12-3 stuff, so it's just some geometric probability. Okay. The rest of them, it's 12-4. Most people were done with it before they walked out of the classroom. So you gotta open up your book or something like that, you'll get it done in no time. Okay?
My notes.
It's fine.